Great. So after Dennis' introduction, we are left to prove that this is that we have an equivalence between these two factorizable categories. So we'll first construct a functor in one direction. Factorizable functor. And the direction I choose is the one from right to left in this board. And then discuss how to prove it is an equivalence. And in the second part, in the proof that it's an equivalence, that's actually how that's actually an example of why factorization categories are so important, because we'll use some result in the theory of factorization categories. Okay, so how do we construct the functor? The functor notation is L for Langlands Whittaker. So the construction will proceed in two steps. First, and then I need to reverse the steps. So construction. First, I use the naive Satake. To map. Yes? No, that's the notation that Dennis introduced.
The one that Dennis. Okay.
So let me say explicit. So width is for relative to G. Maybe that should be also in the notation to emphasize that we have Langlands duality. It's the factorization category. So I give you an assignment for any finite set I. I have D modules on this twisted omega twisted Grassmannian over the power xi, and then you have meromorphic jets over xi. So maybe in Dennis' notation that was something like this character. So that's what, and there is also a twist here. But so I'll ignore the twists, perhaps. I'll forget them. But that's what width is. Okay, so we use the naive Satake first, and that's where the real Langlands duality is. So I go from rep G check. So have a monoidal functor of infactorizable categories. That sends rep G check the naive Satake, as it was discussed, sends rep G check to the spherical guy, the spherical factorizable category for G. That's a functor between factorizable categories. Moreover, it's monoidal, but it's not an equivalence. Of course, remember that. All right, so that's the first step of the construction. That's where Langlands duality is. And now I need to move from the spherical factorizable category to the Whittaker category. And I'll do as follows. So I'll note that spherical for G, so it's monoidal and acts on Whittaker. I'll explain that in a second. And then, so assuming that the second step of the construction will be from spherical to Whittaker, again for G, and it's the functor of action on a specific guy that I call J min. So where J min is some specific guy in Whittaker, some object in Whittaker run. So that's the plan. So again, 2 steps. First, I use the naive Satake, and then I have a nice object in the Whittaker I like, and I act on it by the spherical. So what's the action? Just as a reminder, action of spherical. So I have an action spherical on the Grassmannian. Let me say for h power of the curve. Action spherical on D modulus on the Grassmannian. Actually, I can think of. So this was explained by Dennis in his talk on the 3rd day, that he drew some diagram convolution. But another cheap way to say it is that you can write spherical as an endomorphism category. So the category endomorphisms that are g of k I linear in D modulus on the Grassmannian. It's also explained in Dennis' notes. So, because what I'm doing, say pointwise, so I want to do something like that. Yeah. So what? Let me not explain, but so you can easily write the spherical as an endomorphism category, and then it obviously acts on this, and moreover, on the other side, I have an action of jets for G, and in particular, n jets. Meromorphic n jets. So that gives me the action. So they have an action of this on this, in particular, I have an action on this on the Whittaker category, because this is a bimodule. And so I should mind twists here, but twists. So because everything was twisted, but let's not discuss this. So it's not a problem at all. GOK invariance. So maybe let me explain. So this is. So what I'm writing is, I'm writing, what to say, so there is something to say here, but I'm writing functors from the Grassmannian to the Grassmannian that commute with respect to the action of the jets. It's not tautological that this is the spherical. So you need to use that this guy is dualizable as a module over this, and it will work.
Define the action of G of k on this category and what it means for such gadget left, or do we trust?
Well, I can say, so the difficulty is the D modulus on jets. So by modulo that, you have the GOK acts on the Grassmannian by multiplication, and then therefore D modulus act. Just you have a diagram of spaces, you take D modulus with push forwards, and you get it. All right, so that was explaining this action spherical on Whittaker, and now let me define this main object, J mean. So now definition of J mean. So J mean, by the very nature of what Whittaker on run will be a collection of J mean on each power of the curve. So that will be in the Whittaker for G on that power of the curve, and I give 2 constructions, and they complement each other. Construction 1 So I need some ingredients. I have the Grassmannian for n over, say, so let's construct J mean on one power of the curve, and then I need to show that they assemble into something of the run space. So for that power of the curve, I have a locally closed embedding of the Grassmannian for n into the Grassmannian for g. Let me call it j, little j. That's the first thing. And then I have, so my character, my non-degenerate character that was going from n jets of k over xi into ga. That was the residue character, and since it was a residue character, it's null. It's 0 on n of O, regular jets. Therefore, I can pass to the quotient of nk on n of O. That would be the Grassmannian for n, and the character factors. Let me say chi hat. I factors because it was trivial on n of O. And now I have all the ingredients to define J mean under the first construction. So J mean on xi, by definition, is, so you take the exponential d module that appeared yesterday on G of A, pull it back to the Grassmannian for n along the character map. So I leave it here now on the Grassmannian for n, and then J lower star, J lower shik on here. And of course, it's not clear from this definition that this guy satisfies the Whittaker condition on the Grassmannian. But so let's keep that in our pocket, and let me give the second construction. Can I erase this? Second construction. I have a map from, I have a section map that I call U from xi to the Grassmannian for G over xi. That's the trivial map that associates, it's a section, associates the trivial bundle with the obvious trivialization. So section, trivial section. So what I can do, I can push forward the dualizing sheaf on xi I can push forward the dualizing sheaf on xi to the Grassmannian for G. And now, so that's a D module on the Grassmannian for G, and I want to Whittakerize. I want to force it to be Whittaker, and I do it with average shriek, Whittaker average shriek. Maybe I can. So it's invariance for nk xi against the character. Where what is this? So by definition, so that would be the second construction of J mean. And by definition, what is average shriek? Well, I have an oblivion factor from Whittaker over xi. It's fully faithful oblivion factor to the Grassmannian, to the module of the Grassmannian. And as we defined the other days, I have average star, which is the right adjoint. And now I'm not taking that, I'm taking its left adjoint. Right, so let me erase this decoration. I won't use. So I have an oblivion. So the left adjoint. So by definition, average shriek, left adjoint to oblivion. And note that it's not defined all the time. It's only partially defined, but I claim it's defined on this object. due to holonomicity. So yeah, so the so because see whenever I have so what I'm doing I have to be careful. I have an equivariance with respect to an int pro group. So it's the int part that makes this guy likely to be non-continuous. So I said I have it because I have it for like abstract nonsense, but it's not continuous. So some people say we don't have it. So just we have it for formal reasons. It's not continuous. I won't use it. But on the other hand, due to holonomicity or in holonomicity, because I'm on the Grassmannian, I claim I have this. But yeah, so maybe you are pointing something that is coming next, that this guy's clean. So I can put a star here. I'll get to that.
The question does it have any coordination to the middle board?
So I'm very scared to put av star.
No, but it will be totally off. It will be just chronological dimension. So let me just comment to Sasha. Forget everything. Consider just int a infinity, okay?
Okay.
Which acts on itself. So, okay, what are we doing here? So you're considering equivariant D-modules. Let me give an example. It's the dualizing. So how is it gotten? You can take the delta function and Schwick average it. It's really the Schwick averaging. Okay. So that's the guy you want. So now what you, okay, now you can so if you take delta function, try to take the star average, you will get so something that looks like a constant sheaf, and that lives in a very, very wrong because a very, very wrong homological dimension. It's first of all, it's a pro object, and it's a pro object actually 0. So
Dennis, the object is very nonplussed, right?
Pardon me?
So, it's very nonplussed in the old story of D modules on the Grassmannian.
yeah, so okay, so I see a very good question. So like you're considering, so when you put
It
this
sits on same infinite orbit, right?
yeah, it lives. Yeah, forget even like yeah. So it lives even when you live in one orbit. When you impose this n of k equivariance condition, you completely lose finite dimensional support. It lives in first of all, it has infinite dimensional support because it supports the entire object, entire orbit. Also, these objects, all of these objects are 0 with respect to the canonical T structure.
Yeah, that's what.
So they're all cohomologically nil. Like the dualizing A infinity has no cohomologies. And so that's the reason this category hasn't been considered before, because people were afraid, people were uncomfortable with, well, because people were trying to build things starting from abelian category, people were uncomfortable with objects which have 0 cohomologies. And so that's kind of, yeah, Sam, what's your comment?
Sorry, but
This category is defined in your paper as GKB.
Not to define Grassmannian.
Yes.
sorry, but our convention from the beginning was that we considered the DG categories were all objects which are quasi-isomorphic identified.
But no, what do you mean? What do you mean quasi-isomorphic? There's no such thing.
Yeah, I mean.
Can I move on?
I mean,
Yeah.
different mode of the derived category.
But there's no T structure. Like, so you can have a T structure, but these T structures don't have to be separated. So, like, you have objects which are all of which cohomologies are 0 with respect to the T structure. The object is not 0. Like an int code, that's different between int code and quasi-code.
Okay, so let me comment on why these two constructions give the same answer. I think it's okay to give a fine-dimensional toy model. So why are they the same? So let me say that in a fine-dimensional situation where I'm not relative to anything, here I'm relative to xi. So let me say that, say X is a fine algebraic group acting on Y, so Y is a scheme, everything finite type. n-dimensional group. So what am I doing? On one hand, I'm taking, so as we know, this action yields an action of H on the modulus on Y. So what am I doing? The second construction just here is the construction of average streak. So say also you have a character, average streak. So let me say H chi of a delta D module at little y, where little y is a point. And then I'm claiming that tautologically this is equivalent to the inclusion of the orbit, of the H orbit through y into big Y, shriek of this object, which is the pullback under this thing of X, where this thing is something that goes from the orbit through Y into GA, and it's defined as follows. Take an object is n times y, or h times y rather, and you say take chi of h. And then you should raise an objection, because maybe this is not defined. This is only defined whenever, so because I have stabilizers, so whenever chi restricted on the stabilizer of little y is trivial. If I have this, I can do that, otherwise I can't. But it's not a big problem, because whenever I don't have this guy is 0. So sorry? Sorry?
You don't have a map. Not real.
Just, I'm claiming it's just base change. So there you get a map. Just write down what this is. It will be a push-pull, pull along the projection, push, shriek, push forward along the action with the character. You have this delta, play base change.
You write this.
I can write it, but maybe not right now. So just the conclusion, if on the other hand, chi is non-trivial on stabilizer of y, then I don't have this, but this shriek average is 0. So I don't really care. All right. And another thing that this tells me, so similarly, I have cleanness. That's a crucial thing of J mean, aka by definition, i.e. So let's go to the first definition. I have a natural map from this guy, which was defined with the shriek, to the same guy defined with the star. I always have that. And this map is an isomorphism. Sorry? Exactly, because, well, so I go back to the relative setting, but the difference between those two guys is orbits, or it lies within the locus, is supported within the locus where I have this condition. So anything which is, anything in the support of the locus where this is supported will satisfy this condition, so by the character will be 0. So, and that observation allows me to claim that So thanks to cleanness and base change, I can assemble these guys that were defined for any xi to an object of Whittaker run. Like this. So I have compatibility.
Can you explain so why cleanness is what you need? Why do you need cleanness to assemble?
Yes. So I need to check that these guys for some powers of the curve Schrick extension along Schrick restriction along diagonals, and so if I have a
define it with star from the very beginning, that's how you would have that.
in the construction I just erased,
yes.
yeah, I would have that, but then I wouldn't know if that it was in the Whittaker thing. Maybe I could argue that. But so the point of this second construction is that just I forced it to be.
I mean, suppose you do the same with trivial character.
Then I wouldn't have cleanness, right? Because
you would have cleanness, but somehow if you just consider this J low star, then everything would work, right? I mean, you would get an object of your category.
yeah.
I'm saying that if we just suppose that we take a character which is not degenerate,
Zero.
for example 0, but and take J lower star, you would get an object of your category.
Absolutely.
That's base change. Okay.
Not that you need cleanness to be able to define the object.
No.
No, but if I get to the second part of my talk, I will play with these guys. So I needed average anyways.
Sorry, do you mean to say that from the first definition it's not clear that it's in the Whittaker case?
Exactly. But then, after proving cleanness, it's clear. No. So I have two constructions. One is nice with the J level Schrick of character on the orbit. And I also know that it's J level star of character on the orbit. And this description allows me to define an object here. On the other hand, this guy is a Schrick average against the character of something of a delta thing on xi. That's all I said.
Yeah, the second construction implies that you are in the Whittaker category because you're on the nose, you are equivariant, you force equivariance.
Because this lands there.
So then suppose you take a character which is some kind of intermediate character, and define an object by taking J lower star. Will that be in the point category or not?
Yes.
So that means, but it will not be equal to average Schrick. So somehow
It will not be average.
So you don't need this equality to be able to prove that you land on the equivariant category.
For the star, no. For the Schrick.
The Schrick, as Larry explained somehow, unless you have cleanness, is not an object of this theoretical category in the first place.
Yes.
So somehow.
Yeah. For the star, it will be automatic, right?
So finally, I have J mean defining for any power of the curve, and therefore I complete my functor. So that this implies that I finally have accomplished what I said 10 minutes ago, that I have my functor. So I have factorizable functor from rep G check to width. So that was the construction, and now
How did you know that the boundary of this orbit has not driven
just look at what this is.
I assume that's what mean spans. It's like the smallest orbit where I was.
Yeah, so for example, let's say we are pointwise, right?
What is your plan when I
Oh.
wanted to finish?
How much time do we have? 5 minutes?
Something like that. So probably there's no time to answer the question.
Oh, remember, but this will come up in a second. Okay, so yeah, let me just say. So you have nkx orbit on the Grassmannian. are in bijection. So let me call that S lambda, that's nkx on T lambda, that's in bijection with lambda, all dominant, all weights. All weights of G check. But by this observation, only so then I have a bunch of objects of the Whittaker at X that I can construct. They will be supported on the orbits. I can just do average Schrick against nk with a character of delta T lambda Grassmannian. Let's call this J Schrick lambda. However, that's for all weights of G check. However, some of them will be 0 thanks to this. And those that will be 0 are exactly when lambda is non-dominant. So thanks to this. So only J lambda Schrick Schrick is non-zero if and only if lambda is dominant. And that's a consistency check that at least, at the level of objects. So I wanted to prove that Whittaker was rep G check. In particular, Whittaker X should be rep G check, the honest one at X. And I have, at least maybe I can guess where the objects will go. So for a irreducible representation, I will get these objects. And I don't get more, because for non-dominant, I have the character that makes this thing die. So, and basically the proof that this is an equivalence, this constructive functor is an equivalence, actually boils down to the pointwise to the pointwise.
I mean, it's a DG category. What do you mean by objects? What do you mean by, you want some?
I'm running, so what do you mean? So it's a rep G check. It has this structure. Yeah. So far I just define objects there. I can define objects. Why not? So I have this functor. If it's defined because this is holonomic, what's the problem with objects? So let me explain how I reduce this to the pointwise computation that I sketched. Oh, I can call it. So Travis asked a question that made me explain the finishing line without explaining how to go there. But then I use a cool lemma by Dennis about factorizable categories that says that if C to E is a factorizable functor, and so under some hypothesis, what I like to do is what is easy to do maybe is to prove that a functor between factorizable categories is an equivalence on 1 power of the curve. Maybe that's the easiest thing I can do. And so Dennis is providing hypotheses such that this is enough. So if I have a functor between factorizable categories, and for each power of the curve, the source category is compactly generated let me write this functor phi. If this is compactly generated and phi of xi from C of xi to E of xi is proper. I don't know if this term came up, but proper means that this functor preserves compact objects. It sends compacts to compacts. Then the entire functor between factorizable categories is an equivalence if and only if the functor on the first power of the curve is an equivalence. So now I want to prove this, and so the technical part of the proof will be to verify that hypothesis 1, compact generation of rep G check over xi is verified, and also I need to verify that this functor that I constructed sends compact to compact. That's the technical part of the proof, which allows me to reduce to this implication. And the fun part of the proof is to prove that this functor of the single power of the curve is an equivalence, and that reduces to what Travis was asking. And so it reduces to prove that the functor does this.
But that presumably makes sense for functions.
Sorry?
Suppose you replace all D modules by functions.
Uh-huh.
This last part.
So the proof.
The calculation on orbits. Yes.
Yeah. So you want to go back to number 2?
I don't want to go back. I'm just saying that to what extent is this calculation classical and to what extent it's categorical?
The calculation pointwise.
Yes.
Okay.
The
That rep
calculation
check.
for a single point. That the map from.
It's classical. It's basic classical.
Okay.
That's where I want to be.
Okay. So there is a result in number theory that is the analog of this, and then Dennis with Edward Frankel and Vilonen a few years ago proved a geometrization of that, and that's the ingredient that goes into proving that this map is an equivalence. I guess that's all I got. Out of time.